Welcome to continuously delivered scalable geoservices on Kubernetes. A real mouthful, and also a kind of a deep and advanced topic that I'm happy to be here to talk to you guys about. My name is Daniel Fenton, and I'm one of the engineering leads on the ArcGIS Hub team. And some of the things I want to talk to you guys today about is it's not just Kubernetes that allows us to get these continuously delivered and scalable services. There's a whole system of things that are in place to allow us to do that. And what I mean by continuously delivered is that every time we make a change to our code base, that change is approved, it runs through testing, and then is deployed to production. So we end up making sometimes up to 20 deploys every day. Every time something is accepted, we're continuously moving the code base forward. And then by scalable, I mean that we're not sitting there adding machines. Anytime that there's load needs, the system responds automatically, both at an individual service level and at a cluster level. And then Geoservices, the architecture that we run is a microservices approach, so kind of think about it, the Linux philosophy. You have tools that do one thing and do it well. Take the same approach with our services. So we end up breaking things down into a lot of little pieces, all run on the same cluster. So what I want to talk about Kubernetes. I want to spotlight one of our applications that's running on our cluster. That is our spatial download system. And I'll talk about a tool called Jenkins, which runs our CI and CD pipeline that does our builds and testing and actually talks to the cluster to deploy. I want to talk about deployments in general. Because for continuous delivery, you have to have a good bit of tooling around your deployments to make sure that they're safe and reliable. I'll talk about Cubeutils, which is the library that we use to manage our deployments into different environments like dev, QA, and production that we've open sourced. Talk about how those deployments roll out, and I'll talk about how we do our networking and monitoring. So just some quick background on ArcGIS Hub. It is a web application that lets organizations publish content for their audiences, whether those audiences are the general public or they're internal. And one of the goals of this product is to make data more interoperable. So we have systems that translate data from one source to another, making it downloadable or making it work in different API formats or making Google Analytics work in our product. It's been around since 2014, launched as ArcGIS Open Data, has become ArcGIS Hub, and same underlying technology makes up ArcGIS Enterprise sites as well. So it's used by hundreds, that's actually wrong, it's thousands of organizations across different levels of government and private business. So why should you even be in this talk? Why should you even try to do some of the things that we're doing, even though they're quite complex? And I think for us, one of the biggest benefits has been that we have this really quick time from an idea or like a feature being specified and deployment, right? Same thing goes for bug fixes. We can find a bug in production and have it fixed in sometimes less than 10 minutes, right? So really, it's all about delivering value to your customers as quickly as possible. And you can think about it as this benefit is really helps with our left to right flow. And what I mean by left to right is from code into production. But it also helps with the right to left flow, which is from production back into our code and our development. So it helps us get faster and more complete feedback for production because we have been able to add great tooling for monitoring and logging, debugging. It's really easy for us to add a new microservice, especially if we want to break down an application and have it share some code but run in a slightly different way so that it scales differently. If it's failing, it's not taking down other pieces of the application. It's just a couple of lines of code for us to add a completely new service.
Same thing goes if we need to add something like Redis to our cluster. We can literally just copy a YAML file, which is just a text file with some keys and values, into our repository and have Redis running in our cluster with DNS, security, all that. So that's been really, really huge for us. Something that we've taken advantage a lot since we moved to this in 2017. It's given us automated and reliable deployments. So as I mentioned, we deploy tens of times a day, not always that much, but sometimes that much. And we really don't have to worry about the next deployment taking down our system. That's because of not just the Kubernetes tooling, things like readiness checks and liveness probes, but also the end-to-end testing and unit testing that we put into our whole CI pipeline. Gives us a really sweet workflow with Git. And whenever we merge to master, that just automatically goes to production. We know exactly what's in production. If we need to revert a change, roll something back, just click revert in GitHub and merge that PR, and it rolls back, which is really awesome. We always know exactly what's running, right? And it's put scaling on autopilot. Before this, we were running in OpsWorks without auto scaling, and we'd get an alarm and go in and click a few buttons and wait like 20 minutes, and then sometimes the event would be over. In this case, as soon as certain thresholds are hit, either at the cluster level, so we need more actual EC2 instances, or at an application level, we need to run more of the API, or we need to run more of the indexer workers. That just happens automatically. We don't have to think about it. And then it's actually, for us, it's actually cheaper because there are fewer idle resources consumed. So we don't have to provision capacity for the workers for the download system to handle the max that we're going to hit. So it'll, if there's no work going on, it'll scale in all the way down to 1. If there's a ton of work going on, it might go up to 50. I don't even really have to think about it anymore. I don't look at it anymore as long as we're not blowing out our budget, and we're not. I just don't. None of us think about these things, which is a great load off and makes us more efficient as a development team. With that, I do want to start and give you some of the key terminology here for Kubernetes. So at the highest level, you have a cluster as an operator. That's generally what you're interfacing with. Underneath that, or running in that cluster, there's a cluster autoscaler. And that's actually adding and removing EC2 nodes. You don't really interface with AWS or whatever your hosting provider is when you're running the cluster. You interface with the cluster itself, and the cluster works with your hosting provider. That's actually built into it and makes it really powerful. So the autoscaler is adding and removing nodes, and then those nodes are comprised of your those instances are comprised of master and nodes. So masters are the ones controlling the cluster. There's no real work running on those except for APIs and other things. So there's not a lot of CPU going on with that, not a lot of memory usage. And then you have your nodes where the real work happens. So our APIs, our workers, our logging, everything is running in those nodes in different namespaces, which is a partition of the cluster that can have different security, different networking rules, different people allowed to access. It's just a way of chopping up your cluster so that multiple people are sharing the same, or multiple use cases, not necessarily multiple people, but multiple use cases are sharing the same cluster infrastructure. Dropping down another level, you've got, actually I'll talk about deployments. So a deployment would be like an application. Right, so it's our API is a deployment, and inside that deployment you specify a pod, which is getting pretty close to the running process. A pod is one or more logical processes that make up an application. So we have our API pod. It's running in our deployment. The deployment says run this pod with these environment variables, with these labels, expose these ports, things like that. And then we specify a horizontal pod or horizontal pod autoscaler. And that's what's based off of rules saying how many of these things should we be running at a given time. Right? If we want to keep the fleet CPU usage under 50%, like for our APIs, so that we run all of our APIs in nodes. So you want to keep the CPU not busy. That means you can handle tons of requests. So anytime the CPU goes above 50, add another pod. That's what the horizontal autoscaler does. And those can work based off of CPU or memory or even custom application metrics like when the queue is really long, add more. There's a service, and that's like DNS. So the service maps a name onto a deployment so that anywhere inside the cluster you can reach that service. So our API talks to Redis at redis://redis because there's a service on top of that. And then there is an ingress. So ingress is what maps traffic from outside the cluster to inside the cluster. So you'll say at /API/v3, go to the v3 API service. At v2, go to the v2 API service. So how does one acquire a cluster? There are a lot of different ways to do this, and a lot of exciting competition in this area. Basically, all of the major cloud providers have embraced Kubernetes. It came out of Google. It was initially a project called Borg, and then they created Kubernetes as kind of the next generation open source version of that. And Google called GKE, or Google Container Engine, has like fully managed Kubernetes. Click a few buttons, you get a cluster up, master and nodes. You can upgrade really easily. It's a really sweet service if you can work on Google Cloud. And then there is AKS, that's Azure Kubernetes Service. So Azure actually hired the guy who created Kubernetes. So Microsoft is like seriously all in on it, along with Google. And their service is really awesome as well, fully managed and worker and nodes. And then they have something called, I think it's called their Container Engine, where you can run containers in your Kubernetes cluster, or at least logically in your Kubernetes cluster, without actually having any instances. So abstracting away even further, you don't have to think about running nodes or anything like that. You just think about your workloads and your networking and your logical application rules. So that's a really awesome service. AWS has EKS. That's their Elastic Kubernetes service. And that one is coming along, but it's only partially managed. So it handles the master nodes and like security in those with AWS IAM, which is really nice, but it doesn't manage any of the worker nodes. So you still have to bring your own worker nodes. It's not as easy. You have to have a little bit more tooling. The tool that we use is called COPS, because we're heavily on AWS. But COPS is an open source CLI that lets you build a cluster. You say, I want this version, these nodes, and kind of specify a YAML. It's kind of taking the ideas of Kubernetes and at the application level and bringing it to the cluster level as well. And so we use that tool to operate our cluster. There are many other ones out there, but I think those are kind of the top ones that you should know about if you're running in a cloud. You can also run Kubernetes on premise, but I personally don't have a lot of experience with that. So this is kind of like the external view of our cluster. So we have everything running inside of VPC, which is virtual private cloud. It's our network within AWS, and within that are all of our master nodes spread across 3 availability zones. An availability zone is it's a data center. So it's inside a single region, but different data centers, and this gives us high availability. If we need to upgrade our masters or one AZ goes down, you have a network partition, we could still access the control plane and make deployments, change things about our applications. And then the nodes are running in those same AZs. And then we use external services in AWS, like RDS and Elasticsearch. And I want to point these out because one key to our success with Kubernetes is that we don't put stateful things in there. or we do, but they are things that we don't care if we lose. So like if we lose our logs that are in a different Elasticsearch inside the cluster, that's okay. But if we lose our search index, that's going to affect our customers. If we lose our jobs table, that's going to affect our customers. So those are run on external managed services by AWS, and that just gives us a lot more kind of security and stability. They have automatic backups and things like that. Kubernetes is running, at our application level, all, as I said, stateless applications that you turn off at any point. They kind of share nothing except for these backends. Inside our cluster, we have things broken up into namespaces. So at the bottom level, there's the system. This is a level that developers should pretty much never be touching. We have our external DNS here. External DNS is mapping our AWS load balancers, which on that last slide you saw, load balancers, how the cluster connects to the internet. External DNS is mapping the load balancers to our actual domain names, because we might actually spin up and delete a cluster at any time and just point to it by a domain name. There's always a random name for the instance of this cluster, but there's a permanent name, prod.cluster. But that might be, funnywave.geocloud.com or something like that. So we can spin those up and tear them down. But they maintain the same name, the same interface for our external networking, the same interface for our developers. They go to the same URL, even if the cluster completely changes out. We have the cluster controllers in there that are actually scheduling things, saying this many pods should be running over here, this many over here, this job needs to run now. That's not something we actually touch. It's part of the system. We have the cluster autoscaler that's in here, looking at utilization on the actual EC2 instances. And then adding and removing nodes. And then there's internal DNS, which is how those services, as I mentioned, the API talks to Redis at an address called Redis. The internal DNS is managing that, and then the actual cluster API is in system. Only things in system actually run on the master nodes, and not all of them are actually on the master nodes. But anything above is not running on master nodes. It's running, except for some of the logging, it's running on those worker nodes. Monitoring, and we have a lot of monitoring tooling, and it's a big part of why we're able to be successful, deploy very quickly, and debug very quickly. So we have running, it's not actually ELK, it's Elasticsearch, FluentD, and Kibana. So FluentD is collecting logs from all of the different things that are running on the cluster in every namespace. And it is feeding that into a different Elasticsearch instance than the one that we use for powering the actual customer-facing application. So that's pulling in all the logs. And then Kibana is running, which is a tool for us to analyze those logs. So search, look at what's happening in different namespaces, what's happening in different applications, what's happening for traffic coming in. Basically, everything that's going on in the cluster is going to feed into this Elasticsearch logging and Kibana viewing. We've got Prometheus running, which is a tool that lets you collect and analyze time series metrics. So how many indexing operations did we run last night? How many of those were saved by our hashing tool? It lets us analyze the performance and see kind of what's going on. Then we have Grafana, which we build dashboards for common views that tie into Prometheus. So show how many jobs are we running, how is this deployment growing and shrinking, but also looking at Elasticsearch and saying what were the top HTTP refers into our API. How many 400s are there? How many responses over a second are there? Alert Manager is tied into Prometheus. And basically, we have a set of rules that say if the API, P99, the 99th percentile is under, is over 300 milliseconds, then alert us.
maybe just send a message into a Slack channel and let us know we should check something out, or actually page us, so pager duty. Really just into a different Slack channel and onto our cell phones. We're not carrying around pagers, but it's critical that we have kind of the robots doing work for us and making sure that the cluster is running as it should be. And then there are various scrapers that feed into Prometheus. So scraping Elasticsearch, scraping Nginx, and putting data into Prometheus so that we can analyze it. And then the next level up is the ingress namespace. That is just runs Nginx for the cluster, and it handles those ingress resources. So Nginx is really, really powerful, fast, and kind of hard to develop on web server, but it's awesome. And it handles all the traffic going into our cluster with very little CPU or memory usage. So when we have /API/v3, you would hit an ELB, and then you're going to hit Nginx in the cluster, and then it's going to go to the service. So it's kind of like a traffic cop. One level above that, we have a different namespace for some sensitive apps. One thing that the Hub product does is lets you have custom domains. So like opendata.dca.gov works via HTTPS because we're running Let's Encrypt certbot in this sensitive namespace, and it's actually generating certificates. But certificates are important data that we want to keep safe, so very few people actually have access to this namespace, even though it's running in the same cluster. So people can't get in there and steal certs because they do not have the access. And then there's the apps tier. And this is what developers are thinking about most of the time. We've got different APIs in here, different workers in here, job managers. This is a really simplified view. I think we're over like 10 different services in this apps tier. Yeah. Cool, so just like a spotlight, one of our applications that runs in here, we have the geodata download system. This is doing is it's pulling in data from ArcGIS Server via whatever means necessary. If it's an old server, it might be ask for all the object IDs and then scrape through those. Newer servers using result offset, even newer servers that have extract turned on, importing from file geodatabases. But it's sucking data into our system that mostly we use to translate into different downloadable formats that we keep cached, like GeoJSON, KML, CSV shapefile, and GeoHash for visualization. We plan to use this for other things like automatically generating vector tiles or being able to search within datasets. But this is our kind of big time system that's scraping literally hundreds of thousands of GIS servers every day. And these are kind of old stats, but we're actually up to 25 million downloads per year out of this system, and probably well over a terabyte per month. The workloads are really spiky. So it runs on a delayed job system that refreshes data in the background because data changes and needs to be kept up to date. So ArcGIS Hub users request data from the API. It's going to pull it out of S3 if that's available. If it's not, it's going to do some things with Postgres to schedule jobs. The job queue is actually run in Redis, and they're import and export workers. Import workers pulling data out of ArcGIS Server and writing it into S3. Export workers are pulling data out of S3, translating it, and writing it back to S3. It's all running in streams, very efficient, but sometimes we need to run like 50 import workers or 50 export workers at a time, really scale up the cluster. Cool, so that is maybe too small, so I'm gonna go into the actual repo and just zoom in. But at the root of all this, all of our applications are specified in Docker files. So I won't go through every line of this, but the general idea is that we specify a runtime, some environment variables that are kind of always there. We load in our custom builds of GDAL, install a bunch of dependencies that we need for our application, set up locales and things, actually install the node application in there. It looks complicated because we run a what's called a mono repo, where you have multiple packages, node packages, in a single repository. And if you want to have a mono repo and still use Docker's caching, you're going to have to do a little of this gymnastics. But the thing is that once you build the Docker file, you can deploy it, n times on the cluster, and it's always the same thing. You know for sure that it's the same thing. Well, that was one of the reasons we moved off of OpsWorks, because with OpsWorks and Chef, unless you're using other tooling, you are actually doing a build every time you try to deploy a server, and that is really slow. It's prone to error. What if the what if the package registry is down? What if there are sunspots? Whatever thing, right? Your application can't build, you can't scale, people are mad. But the Docker files, it's exactly specified. We know exactly what the dependencies are. And the cool thing is that when we pen this, actually some of our other repos are only penned to a node major version. Every time we build, we'll pick up security updates and things like that. And because we're deploying so many times a day, our apps are always up to date. And then, so those three services, back a slide. So the API, the import workers, and the export workers, even though they are different things, they're the same code base and they're the same Docker file. You just give it a different command. Same thing goes for our search and indexing repository. There are 7 services in that all use the same Docker file. They all kind of deploy together. It's just, when the file starts up, you give it a command. It's which one am I going to be today? Am I going to be a worker? Am I going to be an API? But it's the same code base, and that may make for larger Docker files, but it sure makes for easy development and speed. Cool. So the continuously delivered part is where Jenkins comes into play. So as I mentioned, every time we merge to master, Jenkins, I didn't mention Jenkins, but Jenkins is the application that actually does the build and runs tests and talks to the cluster directly. So most of the time, our developers don't actually talk to the cluster. They might use some web tooling that's on the cluster, but they're just thinking about the application code. All this stuff is abstracted underneath them. They don't have to think about it. So Jenkins is our CI server. We run pipelines. We store some secrets in there that are used to actually communicate with the cluster securely. It runs automatic jobs. So every time there's a pull request to our code base, it'll run unit tests and linting and validate that any configuration changes are going to work. And then on merge, it'll actually deploy. And then nightly, it'll keep our dev cluster up to date. And then there are on-demand jobs that we run out of it. So one-offs, things like that. This is our pipeline. I think that's maybe too small, too. So let's see if I'll just zoom in on that. So this is what things look like on a merge to master. So first things first is we're going to install the dependencies that are needed for running the application and testing it. It's actually this isn't really the actual application install, although it uses the same Docker file, so we know it's going to be the same. But it's installing all the test dependencies as well. So it's going to run unit tests and do those validations that I mentioned, and then it builds the Docker image that's going to be used for deployment in any environment, dev, QA, or production. And it pushes that to our secure repository, which is AWS ECR, Elastic Container Repository. And then it will trigger a deploy to QA. So as soon as the unit tests pass and a build is successful and the configurations are validated, we go right to QA. And then if that is not successful, automatic rollback. So a deployment might fail because the API didn't start up correctly. Well, probably not because we have great unit tests for that. But if the API wasn't working, we have what's called a readiness probe, which is checking to see if any application is ready to serve traffic or do its work. All of them have readiness probes. If any one of those fail, so there are literally 5 services rolling out anytime we make a change to either of these applications, it's going to roll back the whole thing. So automatically go back to the last version. We know, we don't have to do manual cleanup. So if that's successful, we will do our integration testing. So that's actually doing things against the deployed QA application. Maybe it's making a change in ArcGIS Online and seeing that filter all the way through to our index, or maybe it's going to see if a download in a filtered version works correctly, if it'll update after making a change. It's really exercising the full gamut of the system. And I cannot stress how important these are for making rapid deployments confidently. We know that we can deploy 20 times a day because we're so confident in our integration tests. And it means that we don't regress very often because we have really good test coverage here. So when something goes out there and it stays running, we know that it's going to be good, and we're pretty much always moving forward. If those integration tests fail, it'll roll back QA. So it'll just go back to the last state, and we can either make another PR to fix that, or we can revert and then go from there. So if those pass, we will then deploy to production. Same thing with that QA step. If the deployment fails because one of those readiness probes failed, or it timed out, we'll automatically roll back production and QA. So everything is as it was before. If it's a success, it's done. And so we're getting, go back to the slide presentation. We're getting messages like this in Slack. So in our notifications channel, which actually no one pays attention to anymore because it's kind of noisy and boring, you see lots of these things going, right? In the beginning, we're like, oh, it's great to see all the deployments, and then we're doing so many, it's like, who cares? But we still get these messages. It's nice to see, what was the last tag that was done. If end-to-end tests fail, there are links here that take us right to CI and let us see what failed. And we can actually improve that by just automatically dumping in the thing that failed. So hopefully you wouldn't even have to go into the CI user interface. All right, so I'm now going to go a little bit deeper into how our application is configured. Kubernetes uses, as I mentioned, YAMLs. YAML stands for yet another markup language. It's just keys and values. You can have lists and things like that. It's like JSON, but without all the curly braces. And so we have one for each deployment, I should say. Service is actually kind of incorrect. But there's a deployment configuration for the API, a different one for the import worker, and a different one for the export worker, thinking back to that download system example that I shared. So even though they're the same Docker file, they're the same code base, they're run differently. So they may have, they'll all share the same image, which we actually use templates here. So the image tag is injected at deployment time. But they'll have different arguments. So this one, it's kind of small to see, but this one is actually the kube export worker. So the arguments are node bin/kube export worker. Right? So same Docker file, different command. And then there are different resource requests. So what is the CPU minimum, CPU maximum? So the application will not even be scheduled to be run if the minimum resources are not met. And then the cluster autoscaler, thinking about that, this is how developers actually interface with these things that they're really not allowed to touch or don't want to touch. If their minimum requirements are not met, the cluster autoscaler will kick into action and make another node available so that this thing can be scheduled. And then resource maxes at the CPU level, it's just constrained. So we say you can't go over 2 CPU. I'm familiar with Node, it's single-threaded. It runs a little bit over 1 CPU because it's doing some of the things at the operating system level. But we say max is 2 CPU, or else something's gone really wrong. And it's constrained. And then the memory is actually, if it exceeds a certain memory level, the application will be killed and restarted. And that's not a great thing, but because our apps are stateless and they're actually built to be restarted at any time to clean up after themselves, we actually have the memory maxes set before the application will actually blow up itself. So the default node memory max is 1.6 gigabytes. We tend to set our memory maxes at 1.5 so that it'll be restarted and the application will have a chance to clean itself up. and reschedule any jobs, gracefully terminate any connections, things like that. And then there is configuration, so mostly environment variables. What's the name of the Redis namespace? What's the name of the S3 bucket? Where's the database located? These things are, it's okay for them to be plain text. It's not a secret, the database DNS. But then there are secrets below it: the database username, the database password, Elasticsearch username, Elasticsearch password. Things of that nature are in the Kubernetes secret store. Basically, it's just a key value store for things that are sensitive, and you have to have permissions to read it. Your applications can read it if they are given permissions to do so. And then at the bottom of this configuration, we actually write kind of multiple Kubernetes objects into a single file when they make sense logically together. We have our auto-scaling configuration. So that's at the bottom there. And as I mentioned, that'll say keep the average CPU for the whole fleet of the import workers at 50%. If it goes above that, add. If it goes below, remove. And then cool thing about these files is that they are in our repositories, right, alongside the code. So configuration as code is something you might have heard about. That's something that we practice. So if I change an environment variable, or I change something about the auto scaling, or I change one of the template, the values that powers these templates, because they're different QA, dev QA, and production, it'll trigger a deploy. So the application developers get to take responsibility and ownership for their applications in production. They don't have to be ops wizards or know everything about these things are working, but they do need to know what does a deployment look like. If they want to add a service, they want to copy this and change it to run it with a different argument, or have different environment variables or things like that. So as I mentioned on the last slide, we use templates, and we have these different environments for dev, QA, and production. And to manage that, we wrote an open source CLI called Cubeutils. It's out there on GitHub, Esri, github.com/Esri/Cubeutils. And the way it works is that in your repository, you would specify a folder called Kates, and then however you want to organize things within that, you can mix in YAML files. And you can mix in handlebars templates. It's similar to Mustache, familiar with that. Just a nice templating language. On our front end, we do everything in Ember, which uses handlebars. So it's nice to keep the same thing, because we have a lot of full stack developers. So specify, in this one example, you got the config map, deployments, services, ingresses. All these things are in this Kates folder. And then there is a separate file called environments.yaml that specifies the values, not the secrets, but the plain text values that are going to go in. So if we have a different log level for each environment, in production we only log at the info level because there's so much it'll overwhelm our system. At QA, we log at the debug level because we want everything. There are different CPU mins and maxes. In dev and QA, we want to do what's called bin packing, which means you're running your applications with kind of less space between them. You might run into noisy neighbor problems where one application is hogging resources on the actual node. Production, we run with more headroom. So higher CPU minimums, higher memory minimums, things like that, so that there's some more margin for error with these applications. And then the CLI has a few commands. Deploy. So deploy is going to read all the variables out of environments.yaml in another file called defaults.yaml, where it's the same for every environment. It's going to inject them into the templates, read all of the YAMLs and the templates into memory, and apply them to the cluster. And then it's going to watch that deployment and report back. And then it doesn't exit until everything is actually rolled out. So all the tests, or all the readiness probes have passed. Your whole application is successfully rolled out with a single command, even though there are multiple pieces to it. There's a rollback command, which just says, take everything in here and go back, all of the different deployments that are in here. And now there's one, an apply command, which will let you run like a one-off job or one-off configuration on the cluster, but still reading those environment variables, still using those templates. It's been really useful for us. There are some similar things out there now that weren't there at the time, like Case on it.
People also like to use Helm. Helm has some moving parts you have to run in your cluster, and I think it's a little bit overcomplicated, but it's the same idea. You have templates and you have variables that are injected into those templates. So we do our rollouts blue-green style, and that means that we start rolling in the new version while we roll out the old version. So new one in, old one out, and as each new container or pod goes into service, the cluster is running the readiness check, which might be like health Z and see, is this thing able to connect to the database? Is it serving HTTP traffic? If that fails, the whole rollout will fail, and all of the old versions will automatically go back into service. So the scheduler is handling this for us. And we get updates in our Slack channel that deployment has started, deployment is completed. And this is a tiny one, so I'll blow this up. This is an example of what our networking looks like. So at the service level, this is where it said we map a DNS name to a specific deployment. So in this case, it is either the dev or the QA or the prod API. We actually have different names for them in different clusters. Just it worked better for our alert manager configurations. And then, so this let's call it prod Kup API, and the prod namespace is going to talk to the any deployment that has labels app, Kup, and role API, and it's going to talk to it over port 80. Using the HTTP protocol. So that makes it available inside the cluster, also makes it available to map at the ingress level. So here's what our ingress looks like. The basic part of it, says anything over /agol endpoint, which is an internal route, will map to the service called prod-kup-API over port 80. And then we have specific additional Nginx configuration there. It's actually really great to specify your Nginx configuration like this, and to specify the rules in this declarative way versus writing a bunch of Nginx code. So we have some special things in there to do an XL redirect, which is just internally, when someone downloads something and stored on S3, it doesn't actually stream through our API. S3 will stream through our Nginx server, which can handle all kinds of traffic going through it. And so we set up some special configuration there. Most of the time, you don't have to do that. And then this is, it's also a service, but it is specifically an external service. So you can do this as well. And this is one of the cool things about how clusters or Kubernetes actually manages the underlying cloud provider. So if you specify an external service type load balancer, it will actually set up an AWS load balancer for you, or the equivalent in GKE or AKS. It'll do that automatically. So if you say, and we do this for the only for the ingress, because all the other ones are flowing through that. So this service has a whitelist of IPs, which we can specify. We say that we want it to work over HTTP and HTTPS. We tell it which certificate we want to use, and you don't need to do this, but we do it because we are using this external DNS. So the name of the cluster is always the same to our different developers, and it's only accessible over these whitelisted IPs, but it works over HTTPS because we specify the certificate that it runs. So we say, runs on HTTPS, some additional settings, and then all of that stuff with the load balancer is set up. The external DNS application, if you remember down in that system diagram, that will work with Route 53 to say that this load balancer should be accessed at this address. Right, so all that stuff happens automatically. You just do your configuration. And then I'll talk a little bit about monitoring that I mentioned earlier, but we use logging stack of, we have what's called a FluentD daemon set. Daemon set is just, you run one of these on every node in the cluster. and kind of like run it in the background. If a new node comes up, run another one. So FluentD is our log collector that's running on every node in the cluster, feeding in those logs. We have an Elasticsearch stateful set. That means it's backed by EBS volumes. If one of them is terminated or needs to be rescheduled, it'll still have the same data. If we cut over to a new cluster, we'll lose the data, but that's okay. This is our like logging for analysis. We can afford to lose that data. And then we have Kibana in there. And all of these are only exposed in the internal network, and they're behind a GitHub auth proxy, which is actually set up in that ingress namespace. And that's cool because if I add anyone to a specific team on GitHub, and they're on the whitelisted network, they get access to these tools. So they just sign in through their GitHub, and it manages that. So that's really awesome. Then we have our monitoring and alerting stack. We use a tool called Prometheus Operator, which makes sure everything is running. Those are stateful sets as well. But it's even a higher level of declarative configuration. We don't even declare the stateful sets. We just say, run this Prometheus Operator, and it makes sure all of that's running. So this is just a little screenshot of a Prometheus graph of latency, 2 different endpoints, and then an example of an alert that's firing. So yeah, there's a lot more to read about this. So I put some links in the slide, which I will tweet out at DMFinton, and it'll be available as well. But I know I just covered a heck of a lot, so I want to open it up to questions. Sure.
So is this something that's done just in production, or do you also develop locally inside of Docker? And if so, how does that work?
Sure. So the question was if we only run Kubernetes in production, and if so, how do we develop locally? And the answer is yes, we do only run Kubernetes we run it in dev, QA, and production. Locally, we're either developing just on our local machine, or we're using a tool called Docker Compose, which is kind of like Kubernetes. You have different services, and there's DNS in there, different environment variables and things like that. Sometimes we're running in a hybrid. We may just want to run the database and Elasticsearch and other things in Docker Compose, expose those over ports. That way you don't have to install a bunch of dependencies on your local machine, which can be fragile. Make sure you have the same version as everyone else. And then you'll just run like the Node app on your local, like bare metal, and connect into those. So then you have access to debugging tools and restart and don't have to deal with Docker builds. It's really efficient that way. Yeah. Cool.
I saw in one of your slides that you've got all of your infrastructure is perhaps sometimes for the download talking to ArcGIS Server on the back end. Where does ArcGIS Server fit into your overall?
Sure. So the question was about where does ArcGIS Server fit into our overall infrastructure. For us, it's an external dependency. So we're dealing with our customers who have published their data into ArcGIS Hub. We're dealing with their ArcGIS servers. And so we're not running it, and we're not scaling that. We are accessing 100,000 different ArcGIS servers. Yeah. Sure.
Did you guys evolve from using Docker Compose in production and move to Kubernetes? Like, this is a lot, so I'm wondering what evolution
Yeah, sure.
get here.
Yeah, absolutely. The question was, did we evolve from using Docker Compose in production to Kubernetes? And the answer is no. We were using OpsWorks before. The evolution was that I started personally experimenting with Kubernetes maybe 4 years ago, and built clusters using kops and was running some demo servers. Running like our Kube servers there. You don't know about Kube. It's a library that lets you connect kind of any API into ArcGIS, kind of like a translation layer middleman, but sometimes needs a lot of different dependencies. So if I needed to get Elasticsearch running on that, or I needed to get CCAN, or I needed to get like random thing X, Y, or Z to make a Kube provider work, I had my cluster, and I didn't have to ask the ops guy to do this thing and support it and run it like that. So kind of internal experimentation, and seeing that it was really working really well. We got to the point where we wanted to launch some new distributed services, but we knew that OpsWorks, we just didn't want to go that way anymore. We were using Chef, and we're using, the name escapes, Packer to build AMIs, but it was like a really slow process. and like no one likes writing Chef anymore. And we weren't developing in Ruby anymore, so it was really kind of foreign. We kind of got to this point where it's like, what are we going to do next? And at that point, I had several years of experience with Kubernetes, and we ended up just building out automation tooling together to actually launch our clusters. So our clusters are actually in CI. If I make a change to anything for the cluster, that'll get deployed across QA and production and keep dev updated as well. And so as a team, we worked together building this deployment tooling, which meant we were standing up and bringing down tons of clusters, like per day, lots and lots of clusters, automating everything that we needed to in AWS, automating our application deploy, our secret injection. So that process of, as a team, building the automation pipeline helped everybody kind of level up. But then what we found also is that like you don't actually need that many people at our scale and running only stateless apps. You actually don't need that many people that know a lot about Kubernetes. They need to know like how to configure deployment and something like that. But once that all fell into place and we realized we never want the developers to use the Kubernetes CLI, it was easier to bring other team members on board because it's like for them, their interaction with the cluster, and I have some of this up, is at URLs like this. So they go to the cluster and they say, I want to look at the I want to look at the prod namespace if they have access to it, and see kind of how deployments are running, things like that. That becomes their interaction, or they want to look at the dashboards. That becomes their interaction with that. So kind of strayed a little bit from your question a little bit, but did I answer it well for you? Yeah. Okay, cool. So after that period of experimentation, we figured out that we wanted to do this. I think the time frame for us to get this up and running and like get our first production service on it was maybe about 3 months to build out all the automation and then get the first thing. The first thing that we ran in there, besides all the system tooling and the monitoring and all that, was just the background workers for this kube system. It wasn't the API. So that allowed us to build confidence because if the background workers go down, eventually someone will notice, but it's not immediately. So the whole period before we got everything running on that was maybe 8 months, but we had a mature application, right? So with customers and uptime expectations and things like that. So that's why it took us a little bit longer. I don't want to minimize the fact it was definitely a lot of work that required a lot of expertise. But the benefits for us have been tremendous, which is why we're kind of sharing how we do things. Yeah.
So I want to follow up on his question because the title of the talk is about scalable geoservices.
Yeah.
And it's really a download service. It's not really a geoservice.
I disagree with that. So the download system is providing spatial querying and filtering, and powering a spatial GeoJSON API, as well as the search index is also geospatial. So you can search for data that's near me. It's not like in like an web map kind of geoservice, but they are still geospatial and have geospatial at their core.
Okay, then you need to have that engine, right? Is the engine containered inside of that, or how does that become scalable?
What do you mean? Which engine?
Because ArcGIS Server is actually generating the engine to do those queries, correct?
No.
Oh, it is?
No. So yeah. When someone requests like, give me the CSV data for this area on a map, right? Goes through our API, and our API will queue a job for the export worker to it'll pull the data out of S3, and it'll run the operations in memory on streams. So it'll do the spatial filtering, it'll do any of the other SQL filtering, and then it'll write that data back out to S3, and then the API will send it on to the customer.
So the API is hidden back at Esri's?
No. So not in this case. So if someone requests like they're looking at the crime data for DC, right? And they say, I want to download the assault with deadly weapon in Ward 3, right? That's a spatial, also has a where component to it, right? That's how it comes into our system with just like it would in ArcGIS Server. You have geometry predicate and you have the where predicate. And based off the data we've already extracted from S3, we're going to apply that spatial operation. So at that point, we've already extracted all the data from ArcGIS Server. We don't need to go back to it to get the same information. We work on what we've already extracted, which is why you'd never be able to power the terabytes and millions of downloads that we do if you're hitting ArcGIS Server live, including the filtered downloads. Right? So our system is doing that based off the information that's already extracted. Yeah, and actually, I should mention we have an open source library called Winnow, which does Esri, where style and geometry queries, as well as has its own kind of simplified version of that. That's out on GitHub. It's called Winnow. So it's W-I-N-N-O-W. So it does. It's kind of like a SQL database in memory, but it's not meant for storing data. So you say, I have a pile of GeoJSON or Esri JSON, and I want to apply these filters in memory, or I want to apply these filters to a stream, which is how we do it, and it'll do that. So that's running in memory on the export workers as data is flowing out of S3 and back onto S3. Yeah.
So related to that, like, how do you, does your import worker handle finding out if the S3 cache is stale, like where it goes back and imports
sure.
new data?
Sure. So the question was about whether the import worker is handling when things are stale. No, the API is actually doing that. We only have for external ArcGIS servers that don't expose a last edited date, we only have a 24-hour window. So every 24 hours we'll go and update it. It might change, but we have no way of knowing. And then for services that are hosted on ArcGIS Online or otherwise expose the last edited date, we go and check in the background, and then we update it. But that happens at the API level, and then we're actually going to be, we'll be using our indexing system, which is a separate system in our cluster, which does regular like record count checks and things like that to be more proactive about when we go and pull the data into the system. Sure.
So you mentioned expertise, like you experimented. That expertise is within your company, but I'm wondering how much support you got from Amazon. Did you work pretty closely to gain expertise from? You're basically their customer.
Sure. Yes, the question was how much support I got from Amazon in doing this. The answer is absolutely zero. No contact whatsoever. Never even thought to ask for that and didn't need it. I mean, there's so much documentation out there. The way that I would get support from Amazon is that they contribute to open source libraries, right? And that they write they have a really full-featured JavaScript SDK. We write everything in JavaScript, so like even our CLI tooling, our deployment tooling, and all that. So I use their tools a lot, but no Amazon workers were consulted in this go around. Yeah.
Can you speak briefly to how you write and manage your integration tests?
Sure. So the question is, how do we write and manage our integration tests? And in our application, show you one where we have one that's really full-featured. So we have this monorepo, which means we have several packages, but at the root level of the repository, we have a test folder, and this is where some of the integration tests come into play. So each one of them is its own file. It's going to specify essentially like things you want to do, and then wait for the result to happen. So it's still written in JavaScript, which is the language we write our application, do all of our other testing in, and it's just specify essentially step by step what do we want to do, which is we want to create an item, we want to share it, and then we're going to wait. And so we have a lot of these like fetch until, because it's a background job system. So you have a timeout and say, keep doing this until this predicate passes. Most of our tests look like a variation on this. Do something different, at least in this system. Do something different in ArcGIS Online and what comes out on the other end. And yeah, so it goes and gets it, and then at the end it does tear down. So they all pretty much look like that. With the download system, it's kind of it's a little bit different. It's like clear out all the data that might be cached, go and download this thing again, download it in a filtered version, now update the data, see if that comes through, download that in filtered, download it in a different projection, things like that. But it's like all kind of like step by step, usually touch something outside that the cluster is going to react to and make sure that the right thing comes out.
So you just tell Jenkins, go through the integration test folder? Or?
Yeah, so there's a single command. Maybe look at our, so we have scripts that are specified in package JSON, a lot of them, and there's test E2E, which just using the tape test runner says just run everything in this folder, right? And then we have different versions of that for like running them locally, which means run it against a local local API, run the same integration tests. Yeah, I think I got time for one more question. Sure.
Do you have any good examples of your stories and practical implementations of this and as well?
Practical implementations of Kubernetes or of kind of the whole
stack.
Sure. I mean, my best example is our own, for sure. But I think that were we doing this today from like, if we didn't have any of the existing applications and things like that, we probably would have picked one of the managed services, like AKS or GKE, because it's so much more of a button clicking experience. You don't have to know as much about the cluster. You just need to know how to run Kubernetes. But there's some really good how-to guides out there. There's like Kubernetes the hard way, that Kelsey Hightower does. That, I mean, you're going at a low level, but it helps you understand how all the pieces fit together. And then there are like a lot of application, like there was so much copy and paste in getting our tooling up, which is great. Like, because you can just copy the configuration and it runs on the same Docker file and things like that. I'm personally not familiar with others like outside of Esri that are running Kubernetes. Yeah, so my best example is just us. Yeah, okay.
We're looking at doing it.
Cool.
It's going to make it much easier to run one of these operations by a less technical group.
Yeah, exactly.
So networks.
Yeah, you kind of apply your expertise at a layer that then the developers don't need to think about. So we put all this effort into the tooling and all that, and the developers have huge productivity gains. But yeah, so I got to wrap up now, but please take the survey. It's a new talk for me to give at Esri, so your feedback is really important. Thank you very much for coming.